In this video, we're going to talk about the characteristic equation and how do we use it to find the eigenvalues of a matrix. Okay, so the context is going to be, well, let A be a square matrix, so it's going to be n by n. So I want to recall from the last section that lambda is an eigenvalue of our matrix A, if and only if the equation A minus lambda I times the vector x equals 0 has a non-trivial solution. So we saw this in the last section. Okay, so I'm going to state what this is equivalent to. So another way I can think about this. So if this homogeneous equation has a non-trivial solution, that means our matrix right here, so this matrix in front, A minus lambda I, that matrix is not invertible. If there was a non-trivial solution to this, that would mean that there's a free variable in this matrix. So it would not be invertible. Okay, and if it's not invertible, let's restate this using determinants. That means that the determinant of A minus lambda I equals 0. And it'll turn out that this is the key right here. This is the key to how we will find the eigenvalues of a matrix in general by using this determinant equation. So we're ready to define the characteristic polynomial. So the characteristic polynomial of a matrix is the determinant of A minus lambda I. So this determinant that's showing up on the left-hand side of this equation. So our method to find eigenvalues is we are going to solve this determinant equation. Determinant of A minus lambda I equals 0. We'll solve this for lambda. And this equation is called the characteristic equation. So the characteristic equation has the characteristic polynomial on the left-hand side, this determinant, and then it's got 0 on the right-hand side. So we're solving this equation for lambda. So let's do an example. Okay, so let's suppose that A is the following matrix, and I want to find the eigenvalues of A. Okay, so to find the eigenvalues, the first thing I would need to do if I'm going to use my characteristic equation is I need to write down A minus lambda I, what this matrix is, because then I will take the determinant of it in the next step. Well, so lambda times I, lambda times the identity matrix, would be the identity, but after I've multiplied each of the entries by lambda. So that'll put lambdas on the diagonal, and in this case it's 3 by 3 because my matrix A is 3 by 3, so I have to make sure that their sizes match up, and then everything else is going to be 0 still. Because 0 times anything, 0 times lambda, is still going to be 0. Okay, so if I do A minus that matrix lambda I, what will happen is each of these diagonal entries, so the 1, the 5, and the 2, they all get subtracted by lambda. So I'll get 1 minus lambda, I'll get 5 minus lambda, and I'll get 2 minus lambda. But then all the other entries get subtracted by 0, so they don't change. So I'll still have negative 1, negative 7, 3, 3, 0, and 0. Okay, so I set up this matrix A minus lambda I. Now I want to take the determinant and then set that determinant equal to 0. So let's take the determinant of A minus lambda I, and then we'll set that equal to 0. Okay, so we'll set this equal to 0. So if I want to find the determinant, we can do this, for example, with a cofactor expansion. And if I'm going to do a cofactor expansion, I want to expand along either a row or a column that has the most zeros. So the best choice is, let's do the third row. The third row, because the third row has 2 zeros in it. Okay, so if we do that, this determinant becomes, so I know that I'll have a couple terms with zeros, which will just end up being 0. The only term I really care about is this 2 minus lambda term. So what's the sign of that 2 minus lambda term? So for the time being, let me just write down 2 minus lambda. So the sign would be, so starting with this term at the top, the sign is plus, minus, plus, and it would be minus, plus. I don't even have to write out the other signs of my matrix. So I would put a plus in front of that. And then this gets multiplied by the determinant that I get when I cross out the row that 2 minus lambda is a part of, and the column it's a part of. So let me just erase those for the time. Well, Let me just go ahead and write down the remaining entries. So 1 minus lambda, -1, 3, and then 5 minus lambda. And now let me go ahead and erase those extra lines that I drew in. Okay, so let's continue to compute this. So what we have now, well, we need to set this equal to 0 and then solve. So we have 2 minus lambda in front. And then to do this 2 by 2 determinant, I'll multiply these two entries first. So that'll give me lambda squared. It'll give me minus 6 lambda, and it'll give me plus 5. And then we have to multiply these two entries, the 3 and the -1, and subtract that. So I'll have to subtract -3. And this is going to be equal to 0. So simplifying this, we get 2 minus lambda in front times lambda squared minus 6 lambda plus 8 equals 0. So it's getting simpler and simpler. It's getting to a form that we can factor. So we have the 2 minus lambda in front. All right, so this quadratic factors is lambda minus 2 times lambda minus 4. Lambda minus 2 times lambda minus 4. So this whole thing equals 0. Okay, so at this point we are ready to write down our eigenvalues. So our eigenvalues are, so I have lambda equals 2. From actually the first two parentheses, they both give me lambda equals 2. And then the factor lambda minus 4 gives me 4. And those are our eigenvalues. Okay, so that's how we can use the characteristic polynomial. That's how we can use this characteristic polynomial to find the eigenvalues of a matrix. Okay, so one thing I want to notice about this example is, notice that one of the eigenvalues sort of showed up twice in terms of how many factors contributed to it. There were 2 of these factors, the 2 minus lambda and the lambda minus 2, that both contributed to the same eigenvalue, 2. But there's only one factor that contributed to the 4. So I want to define a term that refers to how many factors there are that give me a particular eigenvalue. All right, so this is called the algebraic multiplicity of an eigenvalue. Okay, so if k is an eigenvalue of my matrix, then the algebraic, whoops, I have a couple of typos here I'm noticing. I misspelled algebraic. The algebraic multiplicity of, whoops, I meant to say k. The algebraic multiplicity of k, whatever my eigenvalue is, what that means is it's the number of times the factor lambda minus k appears as a factor in the characteristic polynomial. So in the previous example that we did, we had our characteristic polynomial, and we factored it like this. I can actually simplify this a little bit more by factoring a negative out of one of these two terms in the front. For example, if I factor a negative out of this, the negative will come to the front, and then it'll change it to lambda minus 2. So I'll end up with lambda minus 2 squared, and then I have times lambda minus 4, and I'm going to write the lambda minus 4 being to the power 1. Okay, so lambda equals 2 has algebraic multiplicity, let's put this in a different color, 2, because that's the number of times lambda minus 2 appears as a factor, because that's the power lambda minus 2 has. Lambda equals 4 has algebraic multiplicity 1, because lambda minus 4 just appears as a factor once. And I see that because its power here is just 1. Okay, so this notion of algebraic multiplicity of an eigenvalue is going to be especially relevant to us in the next section, 5.3. Okay, so at this point I want to state a couple of facts. Okay, a couple of facts about the characteristic polynomial and about eigenvalues. So the first is, if A is an n by n matrix, then when we compute the determinant of A minus lambda I, that is going to be a degree n polynomial. So for example, in the example that we did, where was it? Where's the example that we did? In the example here that we looked at, we had a 3 by 3 matrix. And it makes sense that when we computed this determinant, notice that lambda was appearing in 3 spots. In this first diagonal entry, the second one, and then the third one. So when we expanded that thing out with the cofactor expansion, I ended up with a degree 3 polynomial. That would actually be easier to see if I distributed the 2 minus lambda into this quadratic, but this is a degree 3 polynomial. Okay, so let's go back to our facts. Okay, so in general, if we have an n by n matrix, we would have a degree n polynomial for the characteristic polynomial. And the second fact is a fact from algebra, which is if we have a degree n polynomial, that has exactly n roots. So by roots, I mean values of lambda, such that our polynomial is going to be equal to 0. So that's what a root is, something that I plug into a polynomial to make it equal 0. So this is true if we count repeats. So that's like in this example up here, lambda equals 2 was a repeat. It occurred twice. And if we count complex roots, so complex solutions. Okay, so these two facts together, 1 and 2, together they imply that a matrix can have at most n distinct eigenvalues. So our matrix A can have at most n distinct eigenvalues. It can't have more than n different eigenvalues. Okay, so I want to briefly comment on complex roots and complex eigenvalues. So let me draw an arrow connecting this to this note. It's definitely possible for a matrix to have complex eigenvalues, even if its entries are all real numbers. So let's look at an example. So let's say that we have this matrix, 0, 1, negative 1, 0, and let's determine its eigenvalues. Let's look at the characteristic polynomial. So first I'll write down a minus lambda I. So if I do a minus lambda I, just like we did in that last example, what will happen is the diagonal entries get subtracted by lambda. So the zeros get subtracted by lambda. So I'll have minus lambda, and then the other entries will get subtracted by 0, so they don't change. I'll get 1 and negative 1. So now if we look at the determinant of this, the determinant of a minus lambda I want to set that equal to 0. So the determinant of this 2 by 2 matrix, so if I multiply the negative lambda times the negative lambda, I get lambda squared. And then I have to do minus the other two diagonal entries multiplied. So 1 times negative 1 is negative 1. And I want this to be equal to 0. Okay, so this gives me that lambda squared plus 1 equals 0. But if lambda squared plus 1 equals 0, that means that lambda squared equals a negative 1. So this is only going to have complex, or in this case, purely imaginary roots. The answers are going to be lambda equals plus or minus I. Right, because if I take I and I square it, I'll get negative 1. But also if I take negative I and I square that, we'll also get negative 1. So for the time being, we won't talk about matrices with complex eigenvalues a ton, but we will see these more in detail when we get to the differential equations part of the course.